Okay, so if we're looking at electrical resistance, it's obviously like something, resistance in any regard would be something opposing, like I say, if we're applying a force like frictional resistance, right? That would be opposing the motion of an object. So friction or like resistance in a circuit is just friction for a circuit, right? So it's kind of like it's impeding the motion of the electrons, right? It's slowing them down a little bit, right? Or causing them to lose energy, if you will. So let's suppose you're riding your bike down a smooth road and then you encounter some mud. You would immediately notice that it becomes more difficult to maintain the same speed. In a similar way, all matter has some resistance to the flow of electric current. Okay, so along those lines, that's what I was just saying, right? Like it's either going to cause a decrease in energy, which you guys understand now as being kinetic energy, right? Obviously, if we decrease the velocity, we're going to decrease the energy of this person riding their bike, right? And so if we relate that to electrical resistance, it's a property of matter that describes how difficult it is for electric current to travel through a material. Okay, that's just the definition, right? And we've got, like, I don't know, just tried to spell some stuff out for you. 4 main factors that determine the resistance, right? We've got the type of material, right? So some stuff is easier to flow through than others, right? Length of material, cross-sectional area, how big it is, right? Things like this, if you guys are looking at, for instance, if I was looking to build a shop out back, right? And I wanted to have a bunch of machines, you know, for making bagpipe stuff, or a hot tub, right? Those type of appliances, or just the sheer volume of appliances, like you might have 5-6 machines, right? If they're all running at once, you have to have a special gauged wire, right? Gauge meaning cross-sectional area. You know, if you have a bigger gauged wire, it can carry more electrons per unit time, right? Same thing with a hot tub, right? Like if you guys have hot tubs at home, I have no idea. That requires a special kind of wiring, and you actually have to change the panel in your house to accommodate that kind of current flow, right? Temperature, I did a really cool lab in university where we cooled like wires, different kinds of wires with liquid nitrogen, and we saw the change in current flow, right? And so like the colder something got, the easier it was for current to flow through that particular wire, because you guys know on an atomic level, when things have temperature, they like to vibrate a little bit more, right? So if we had a whole bunch of, I don't know, copper or something like that, right? Copper ions or atoms, right? They're going to be like vibrating and bouncing around, right? And at the same time, we're trying to flow electricity through there, right? Well, inevitably, if the copper atoms are vibrating and moving around, well, the electrons are going to bump into them and things, right? And it's going to decrease the speed at which, or it's going to provide some level of resistance for the electrons to flow through the wire, right? Whereas if we supercool this thing, then the atoms kind of stay in place a little bit more, and we get less contact between the electrons and the atoms. And so the electricity flows faster, right? We get more current per unit time. Okay? So that's just the 4 main factors that I don't know, the textbook spells out. Anyway. Okay? And so resistors are electrical components that reduce the flow of electricity going through a circuit at any given time, right? And we need sometimes we need resistors, right? Because if you look at, I don't know, I'm just looking at my laptop beside me right now, right? Like there are electrical components in a laptop, in a computer, in whatever, a TV, right? They can only handle so much current flowing through them at any particular time, right? Or amounts of energy, right, per unit time. Now, what a resistor does is that it's strategically put in, and we're going to look at all these kinds of calculations. Nothing too complicated. We're not building computers, but we're going to look at the basics of, you know, circuits. And what resistors do, well, they decrease the amount of energy going through an electric circuit, right? So they're strategically placed around, important parts of a computer that can't handle huge amounts of energy going through them, right? So they have their place, right? You can't just run whatever you want through stuff and expect it to hold up in the long run, if you will, right? And so we have this thing. So sorry, one other thing. When we move to when we get to Monday and we start drawing some current circuits, you're going to start seeing some symbols, right? And we looked at one. That's the symbol for resistance. We looked at one yesterday. This was an ammeter, right, for measuring current, and we could have voltmeters, right? And these are all things that we're going to attach to the circuit to get readings and things off of, right? And so we have this law. It's called Ohm's law, right? And it says the voltage in a conductor or an electrical wire is proportional to the current if the temperature of the conductor remains constant. Okay, so what we're going to see, this remains constant term or piece, constant indicates, and the temperature being constant indicates that we can represent this relationship linear, in a linear fashion, right? So the higher the voltage, the more current, right? And the slope of this line, remember what we're doing was slope. Slope is always rise over run, right? And so I would be taking the y values, y2 minus y1 over x2 minus x1, right? We're looking at the voltage rise over the current, the run, right? The slope. So the slope indicates where this equation comes from, right? If I just look at this, actually, I didn't want to go there. I want to go right here. We take the voltage and we divide by the amount of current. We get this constant value as long as the temperature stays the same. That constant value is the amount of resistance that we're experiencing. And all of a sudden, we've created this equation for resistance, right? You could also look at, I don't have an in-depth knowledge at the current moment, but I could. We could look at the type of units for voltage and current and how we actually arrive at those units, and it would spit out what we call the ohm, okay, through dimensional analysis. Okay, so I spent so much time and understanding of dimensional analysis. It reinforces where these equations come from. They're just not magic things that, somebody had to come up with this stuff, right? They came up with it by looking at the units, right? Right? Or at least reinforce that they were correct by looking at the units or the dimensions that existed on it, right? I found in a number of situations, right, particularly in the position time graphs or velocity time graphs or the acceleration time graphs, understanding the units that existed on each of those variables helped me in realizing, okay, I got to find the slope here, or I have to find the area. Okay, looking at the units informs which math operation you're going to use. Same thing here, right? Obviously, that's something. If I put a line on a graph, I can obviously, what does the slope represent and what does the area represent, right? That's what you guys got to be looking at, with a critical mindset, where you're looking at graphs and trying to understand them from the standpoint of okay, it's telling me something. As the voltage increases, the current increases. But what does that tell me in terms of, what's the slope and what's the area, right? Well, the slope is resistance, right? So the units for resistance, again, is just we denote using ohm, right, which is the Greek letter omega. Okay, these are a little bit tricky to draw sometimes. You get better at them the more that you draw. But anyway, that's the when you guys give me an answer for resistance, you'll say resistance equals some number ohms. Okay. So if we wanted to calculate the resistance of a load with voltage of 25 volts and a current of 410 milliamps, right? That's what we want to do here. And so we learned above that the slope, if we just look at the graph, right, it's rise over run, which is where the equation came from. So we know that the resistance is equal to the voltage divided by the amount of current. Okay, voltage is an easy one. I see that the voltage lines up, but the problem with the current is it's measured in milliamps here. Okay, so we just got to convert that. We need it in amps. Well, how do I switch something from milli to a base unit of like amps, or like millimeters to meters? Well, there's 1,000 millimeters in one meter. Similarly, we're going to have 1,000 milliamps in 1 amp. So that means we're going to have 0.41 amps of current. Okay, and so to find the resistance in this particular instance, we're going to see resistance is equal to the voltage, 25 volts. I don't know why I wrote 24. 25 volts divided by 0.41 amps. That's going to give us an answer of 61, here we go, ohms, omega. Okay, so therefore the resistance here okay. Anybody have any questions so far? It's relatively simple, okay? Again, I found this to be incredibly confusing the first time I saw this, with all these new units and new, like, what is this thing, and like what's an amp and what's a volt, like what are they measuring? It's a lot of brand new information. So what I thought we would do is take our time with the first 3 lessons here. You know, like here's voltage, here's current, here's resistance. We'll build a little bit of an analogy, right? And then we'll start working with all of them together. Okay. So I don't think the difficulty with electricity is this idea. You know, it's not the equations themselves that are overly complicated. It's when we start mixing everything in and how they all affect one another that things start to get a little bit more complicated. But we have to have an understanding of what the equations are, right, and have some experience working with them. Okay, so we have some consequences of resistance, right? So all components in a circuit have some level of resistance. The main way we experience resistance is the existence of heat. Wow, that's a lot of words with "ents" on the end. It was a mouthful. Okay, in a circuit, some electrical energy, okay, is converted into thermal energy, and you guys will know this if you haven't. Like, the LED light bulbs are not too bad; they don't heat up too much. But if you have an old like incandescent bulb with like a is it a filament? What's the word I'm looking for? Anyway, you guys know what I mean. The little wire running through the light bulb. That's not a filament. That gives off heat, right? It's inefficient. They're not the most efficient light bulbs, right? The LEDs are very good. They're very efficient. They don't give off a lot of heat. But the old light bulbs, not even old light bulbs, but the other kind of light bulbs, you know, they're running electricity through a wire, and then the wire is giving off energy, right? That's how it lights up the room. But in that is also some energy lost to heat, right? Or like thermal energy, and so they're not the most efficient. Both loads on the circuit, and they'll heat up as electricity passes through them, right? That's just one example. A light bulb is just one example of a load or kind of some form of resistance that could exist in an electrical circuit. Okay, superconductors exist and have very low to near no resistance at all, right? And these are able to exist when the material is cooled to very low temperatures, and that's what I was saying before. So in these instances where we've supercooled a wire, right, and we've almost like frozen the atoms in place almost, right? They're not moving around as much. You got to think, every time there's a collision between an atom and an electron, collisions are going to give off heat, right? So if we can cool the material that we're going to run electricity through, it's going to slow the vibrations of the atoms down and increase the surface or the volume of area, oh boy, the cross-sectional area that an electron can flow through without coming in contact with an atom. because the atoms aren't moving as far and not occupying as much space. Okay, and so that's how we would like increase current flow, or at least decrease the inefficiencies, right? Or energy loss to heat and things like that. Okay, so an example of a machine like this would be an MRI, right? Which stands for magnetic resonance imaging. In university, I took so why isn't temperature in the equation for resistance? I think, Jagger, I mean, I'm sure there's probably a more complicated version of resistance that takes temperature into consideration, but I'd imagine anytime we see things change with time, Jagger, this is a whole nother can of worms. We see rates of change. We need to figure out and model how that's changing relative to time. You guys haven't even done derivatives yet, but like we call these integrals in math. Okay, so like it just makes the math more complicated as and then I imagine there is an equation that takes into consideration how the temperature is changing with time and how that affects resistance. But that's a whole nother like can of worms. What they set up here, Jagger, was that we're assuming this equation is assuming that temperature is remaining constant. Okay, so we're not seeing any variations in the temperature, and so we're able to produce this nice linear graph here, where we're not introducing these integrals or anything like that. Okay, or derivatives. Things aren't changing with time in terms of temperature, right? Okay, that was a more complicated answer than I actually didn't know the answer to that till I started thinking about it there, Jagger. Okay, I never really took any thermodynamics. That's not my area of expertise. Most of my physics was in, first, second, and third year physics, right? Where you could like, as you climb the ladder, and this goes for any program, you guys are going to find that you get to pick, you get more of a choice as to what you want to kind of concentrate on, right? The thermodynamics wasn't of interest to me. I like the classical mechanics and Newton's laws and things like that, right? So that's more my bread and butter. But the math concepts and things carry over, right? Something's changing with time. There is an equation to take that into consideration. Okay. So MRI machines, if you guys don't know, well, you're going to learn about it next week. It's a magnetic resonance imaging, right? And so in university, I took like a medical imaging course, and we looked at how we can create magnetic fields by running electricity through wires, right, in a circular fashion. And we produce magnetic fields, and we can use those magnetic fields to align things in our body and take certain images, right? That's what an MRI machine does. That's why you can't wear any metal for an MRI, right? It's because it's magnetic, right? We're running electricity through this big coil of wire. It's creating a magnetic field, right? And if you were wearing metal, it would just get like pulled right off of you, right? I was thinking of something else there to say. That slipped my mind. Oh, you can imagine, an MRI machine. I don't know 100% about an MRI machine because I just learned about the science behind it. But in practicality, I imagine they'd have some form of cooling system in them to keep them relatively efficient. If we're running electricity through wires, I'd imagine they're going to try and keep those wires cool. They don't need to necessarily be like absolute zero cool, but I think the more heat that you have, or the higher the temperature of the wires that you're running electricity through, the more resistance that's going to exist, right? And so that just makes MRIs infinitely more expensive because they're so inefficient to run, right? And so if we can eliminate some resistance, that'll help, right? So that's pretty much it for resistance, right? There's a little summary here as to terms of like what it is, where you can find stuff. One additional thing here is like what it would look like if we were to put on what we call an ohm meter, right? And again, you guys could go to Canadian Tire and pick up like a dial. It'll have a dial on it. You can rotate the dial around. It'll measure all things like it'll measure voltage. It'll measure there'll be a section like you can measure the potential. You can measure amps, and you can measure ohms. Like you can measure all the, you'd see each of the symbols on the actual meter. Okay, they're all on one machine, but I think we depict these things like this so that you can see, okay, what do you want to measure there? It's not, that's different than if I was measuring the voltage, right? It would be different than if I was measuring how much current is running through. That's how they depict it on the circuit, okay? So one last thing before we go, and I just want to finish off. We're going to take everything we've done with this analogy and apply it on Monday, and I think it helps me keep everything straight in my head. And I wish I knew this at university. So it would have might have made the difference that I've actually found this interesting, right? It would have made a change. Maybe I took more of an interest in electronics and things like that in university, right? So resistance, rough road. Again, the R&R. I like this stuff for the reasonings that, resistance is the rough road. So what do again, just to recap from yesterday, we've got a bank. At the bank has vaults in it. Inside the vaults, we have joules. Right? What happens? Well, trucks pull up to the bank. They fill up their trucks with joules of energy from the vaults. And then they go out on their delivery route. Right? But what ends up happening on their delivery route is they run into patches of rough road. Well, as soon as they hit this rough road, they lose energy. Some of the joules fall off their truck. Right? And the idea is, in a circuit, they want to return back to the bank with all of their joules lost so that they can come back and pick up more. Okay, you could even think of like this being somebody's house or something and they're doing a delivery, right? And then if there was another one over here, they do another delivery, right? And the idea is that like the manager at the bank doesn't want to see them come back with joules in their truck, right? They want to make sure that their drivers are getting rid of all the energy or joules across their delivery track, right? Delivery path. Is that okay? That's where we're headed, okay? And we're going to use this analogy further on Monday and put it all together, okay? And then it's a great analogy. I really like it. It just keeps everything in track. Like, I don't know. I like it. Keeps track of like, what is voltage? Voltage is the potential created from the battery. What is current? Current is the flow of trucks or vehicles around the circuit, right? Or a delivery path. And what is resistance? Well, resistance is the means by which the trucks or vehicles lose their energy, or what the work that they're doing. If they're like lighting up a light bulb or something like that, right? Keeps all that stuff straight in my head. Hopefully it does for you guys too. Okay, we'll spell this out more clearly on Monday, and we'll start looking at we'll start building circuits and looking at how do I calculate the voltage here versus the current versus what's the resistance, right? Things like that. Okay, across a circuit. That's pretty much the entire electricity unit for you guys. There's a little bit of magnetism in there too, which I'm going to let you guys read the textbook about. Not too much calculations in terms of magnets. Okay, just conceptual. You guys kind of read about magnets and where they could be used to answer things like what's an MRI and, how do we produce the magnetic field? Which direction is the magnetic field in? Things like that. That's what you guys are going to learn, okay? Does anybody have any questions with what's gone on there? So again, a relatively short lesson there, right? But we're going to put all three of those short lessons together and build circuits. That's what we're going to do and figure out calculations and things like that. At the bottom here, you guys have some questions to work on. Nothing too crazy, just 5 questions, okay? I'll post your energy summative today